Hello everyone, and welcome back to another video example. Now in this video example, we're actually going to be covering part 2 of what we did in the last video, which is a complete analysis or complete linear analysis of an element. So in the last video, we did that complete linear analysis in Mathematica. So we went through all the code to try and figure out what exactly finite element programs do in the background. Well, now in this example, part 2, what we're going to do is we're actually going to use a finite element program, in our case ABAQUS, and we are going to conduct the exact same linear analysis to see, all right, how does the theory compare to the actual FEA program? Now, if you guys are a little bit worried saying, Clayton, that last example, it was pretty long, pretty beefy, I'm not sure I have time for this. Well, don't worry, ABAQUS or any other finite element program is able to achieve exactly what we did before, but much faster. All that nitty-gritty looping and all that other coding, it's already done for us in ABAQUS. So as you guys are going to see, this example is going to be much more smooth, much more fast. And if we do everything correctly, we should get the exact same results as we did with our Mathematica code. So with that being said, let's jump into the example. So I have ABAQUS opened up here. Nothing too special. It's kind of overwhelming at first because ABAQUS has a lot of buttons everywhere. So if you guys are a little bit overwhelmed at first, don't worry, because I always recommend the exact same process and it usually seems to work out pretty well. And that is by following this module tab right here. So if I go to the module tab, as we can see, there's a lot of different things we can do. Now, when I'm creating a model in ABAQUS, what I like to do is I like to just follow the module tab. If you follow the module tab, you guys will always get to the results you need in the end. Everything should work out pretty nicely. So if we look at this module tab, the first thing that we have here is part. So I'm going to click part, and it gives us this menu right here. And we basically have two options to create our part. We have this button right here that says create part, and we have in our model tree over here another button that says part. So if I were to click this button over here, as we can see, we have the create part menu. But if I were to go to the model tree, double click it, well, I'm still back at that create part menu. So it doesn't matter which one you pick. Now, creating parts in ABAQUS is like defining the little pieces of your model. As you guys may know, a lot of models, they have a lot of different pieces. If I wanted to model, say, concrete, well, I know I have to model my concrete beam, and then I have to model the steel reinforcement in the longitudinal direction, and then I also have to model the stirrups, things like that. So in ABAQUS, this part command, this is where you create each one of those separate parts. Now, luckily for us in this linear analysis, we're just analyzing one element, so we're only going to have one part. So when it comes to naming the part, I'm just going to call that element. And we know that we are dealing with a 2D element. So I'm going to click the 2D option over here, and I'm going to keep it deformable and a shell. Now, this approximate size at the bottom here, it actually doesn't really matter. What this does is it basically creates a grid for you to help you create your parts, but it doesn't really matter because we can actually create the parts off the grid if we wanted to. So I'm going to go continue, and this is the grid I'm talking about. So if I were to actually scroll out, we can see that this grid ends at a certain point. That's that approximate size of 200. But again, it doesn't matter because if I wanted to, I can create a part out here. It's not going to make a difference. But what I'm going to do is I'm going to create our element. And what we have for our element is the exact same nodal coordinates that we had last time. So to create these nodal coordinates, I'm going to go to this feature right here, which says connect lines. So basically, I'm just going to go around in a counterclockwise fashion and input all the x and y coordinates of our point. So we know that our first coordinate starts at 0, 0. So I'm just going to go 0, 0. And if I go enter, it already selects that point. And then it allows me to specify the next point. So our next nodal point we said was 3, 1. So 3, 1, enter. I have this point over here. We can zoom in a bit. And then our next point was 3.5, 3.2, enter. And then our last nodal point was 0.5, 3, enter. Now what we actually have to do is we actually have to close out this element. So I'm going to create the final line that goes back to our first node over here. And as we can see, we have now created our element. So by default, we're still going to be in this create lines command. So we're going to exit out of that. And once we're done creating our element, we simply go done. So I'm going to click the done button right here. And as we can see, we now have our nice, beautiful element. But at this point, to ABAQUS, this is just a shape. It has no material properties, it has no loads, nothing like that. So this is going to be the next step, trying to incorporate all the things that we need for our analysis into this shape. So we're going to go to the module command and say, all right, I'm done my part. How about my property? So I'm going to come down to the Properties tab, and as we can see, all the buttons start to change. And this is where we start assigning material properties to this element. How do we do that? Well, again, there's two options. We can go to this button right here that says Create Material, or we can go down to the Materials tab. As we can see, if I click the Materials tab, I get the Edit Material menu, or if I click the button, I arrive at the exact same menu. So it doesn't matter which one you pick. So in terms of material, we know that we're just doing a simple elastic material. So I'm just going to go elastic, and we want to assign it its elasticity parameters. Specifically, this would be the Poisson's ratio as well as the elastic modulus. So those can actually be found in the mechanical tab. So if I were to click the mechanical tab, I get this big drop down menu. And as we can see, the first option here is elasticity. So I'm going to go elasticity, and we know that we are dealing with a simple elastic material. We are not going hyperelastic or anything like that. So we're just going to click elastic, and then we get this nice menu right here, and it wants two inputs. As expected, the first one is our Young's modulus, and the second one is our Poisson's ratio. So just like before, we set our Poisson's, or sorry, I was going to say our Poisson's modulus, but that makes absolutely no sense. Our Young's modulus we just set is 1, and our Poisson's ratio was 0.3. Nice and simple. Now, another thing that we can actually incorporate in this edit material command is the density of our object. So remember before when we did this analysis, we had the effects of gravity, which required density. So in order to specify density, it's actually not in the material tab, it's in the general tab. So if I were to go over to the general tab over here, we can see that our first option is density. If I were to click that, it says, what is our mass density? Well, we said in our analysis that it is simply going to be 1, just to keep things nice and simple. Now we can see that after we define this material, which we call elastic, it has two different things defined for it. First is its elastic stress strain behavior, and then the second one is its density. So we're good to go. We click OK. Now if we go over to our model tree over here, we can expand our materials tab, and we see that we now have this nice material called elastic defined. Next step is, how do I take this material that I defined and incorporate it into our element? Well, there's actually two little things that we have to do. The first one is we go over here to create section. So this can be done either in the create section button right here, or we can go down to sections over here. So I'm going to click section, again, same menu, and it wants a name for our section. Well, the section here is basically our element. So I'm just going to type in elements. We know it's homogeneous, and we know it's going to be solid. So we're just going to go continue. Now, the menu popped up on the other screen, but here it is. And it basically says, all right, if you're defining a section, we need two things. One are the material properties. So this is the elastic property that we've already defined. If we have more than one property, this drop-down menu will have all the different properties. And then the second one is this plane stress/strain thickness. Now, if you guys remember from the analysis, we defined a parameter t, which was that thickness into the page. So what this is going to be the thickness of our element into the page or into the screen. Now, by default, ABAQUS sets it as 1, and in our analysis, we had it as 1, so we actually don't need to modify it. But if you guys were dealing with an element that's, let's say, 5 units into the page, you guys would check this to on, and then you guys can simply switch it to 5. But of course, we are dealing with just a simple unit thickness into the page, so we're going to leave it as 1, and then just go OK. So by this point, we have created our section now, which incorporates both the material properties as well as that into the page thickness, but again, we still haven't actually incorporated it into our element. To do that, we go to this button right here, which says Assign Sections. So we're going to click Assign Sections. It's going to say select the region to be assigned a section. I'm not going to create a set. We'll discuss more about that later, but I'm just going to select our element here. I'm going to click Done, and then this menu pops up. So it says, all right, what section do you want to assign to this element? Well, we only have one section defined, which we called element, so we are going to go OK. Now, if you guys did everything correctly, and you guys want to ensure that your element or whatever part you're dealing with has material properties, it'll turn this nice green color. So if you guys have it as this nice green color, it means everything was successful. If not, it means we have to go back and modify things a little bit. So now that we have the properties all complete, we can go down to the next module, which is assembly. So I'm going to click assembly over here, and we see that we basically have a blank screen. Now this assembly tab, this is where we bring in all those little parts that we are going to use in our model and assemble them together into basically one giant model. This is what's actually going to be analyzed by ABAQUS. So right now we have nothing in our assembly module. This means that from ABAQUS's perspective, we are analyzing absolutely nothing. But of course, we know that we want to analyze our element. So we're going to import our element into this general assembly tab. How do we do that? Well, again, there's two options. From these buttons over here, we can go create instance, which basically means import the part. So if I were to click this menu pops up over here and it says, all right, which part do you want to bring into this assembly tab? Well, we only have one part created, which is element. So we are simply just going to select it and then go OK. Now we see that our part here is now in our assembly tab, meaning it is ready to be analyzed. Another way we could have brought it in is we go down to the assembly tab on our model tree, expand it, and then under instances, we could have double clicked to add more. So if I wanted, let's say 2 elements, I could add that second element over here. But of course, we know that we just want to analyze one single element. So I'm just going to cancel that. And we are going to move on to the next step. What's nice for us is since we only have one part, we only have to do one thing in this assembly tab. It's not too hard at all. So if I were to click here, we see that after assembly, we have step. So the step tab is going to be very important. This is the sequence of events on how we are going to define our loading. So for instance, if I want to take this element and then stretch it, that would be one step. But let's say that after I'm stretching the element and after I'm done stretching that element, I want to compress it after. Well, that would be another step. So all the sequence of events, they are going to have their own step. So what I'm going to do is I'm actually going to unexpand that assembly tree and I'm going to expand our steps tree. So our step tree, by default, we will always have one step created, which is the initial step. And this is basically where we throw boundary conditions. And that's going to be it. This is where boundary conditions go. If we want to load our elements, we actually have to create a step to talk about that loading. So what we can do to create a step is we can, again, click the button that says create step, or we can double click steps over here and we get this nice menu over here. What do we want to call our step? Well, again, this is usually the sequence of events on what we're doing to our element here. So I'm going to call it load element. Nice and simple. Now, we have a bunch of different options for step, of course, but we are going to keep it nice, simple, static linear analysis. So by default, it's static general. We're going to keep that on. But if you guys want a dynamic analysis, something like that, there are options in ABAQUS. So I'm going to go continue, and then we are given this nice menu right here. So basically, we have a couple different things that we can do. We can play with the incrementation. We're not going to touch that. And we have this basic command. Now, this basic command is usually what you're going to deal with when you define your step. And this right here is going to be the thing that most people play with. This NLGeom stands for nonlinear geometry. So if your model has nonlinear geometry, you're going to want to set this to on. Now, most models, and by most I mean most, most models have this nonlinear geometry. So as you're going to see in a lot of analysis that people conduct, they always switch it to on by default. It's always good to have it on, so most people switch it to on. However, and this is kind of going to be the thing for those of you in my class doing the assignment, if we are doing a linear analysis, we are not worried about nonlinear effects. So if we are doing a linear analysis, we are actually going to keep this to off. All right, so we're going to keep it off. And in general, we are not going to play with anything in the step command if we are doing a linear analysis. We are just going to go OK. And as we can see, we have our initial step, and then we have a step called load elements. This initial step is where we're going to apply all of our boundary conditions. And then this load element step is where we are going to apply all of our loads. So after we're done the step command, we can come down. The next one is interaction. So this would be things like contact between two elements, contact between two parts, any cohesive behavior, friction, something like that. Well, we actually don't have that in this model. And if you ever are conducting a linear analysis, you should never really be in this interaction command. Interaction creates highly nonlinear models. So we're actually going to skip that and go down to the next one, which is load. So I'm going to click load right here, and we have a bunch of fancy buttons to basically apply our loads to this element. So I'm going to scroll down here because in our model tree, we have loads and we have BC, which stands for boundary conditions. So the first thing I like to apply are going to be our boundary conditions. So I can select this button right here, create boundary condition, or I can just double click from our model tree. Either way, we get the exact same menu. And it's going to say, all right, what do you want to call your boundary condition? Well, we know that we are fixing some nodes, so I'm just going to call this fixed nodes, nice and simple. And again, these boundary conditions, we usually want to put them in the initial step. It's not going to matter too much if you put it into the load element step, but just for good practice, I'm going to put it in the initial step. Now we have a bunch of different options here. We have symmetry, anti-symmetry, and castrate, which basically means fixed, displacement, rotation, velocity, acceleration. Well, we know that we are just fixing two of the nodes, so we want to make sure that their displacement is going to be 0. So I'm going to select this right here, displacement. I'm going to go continue, and it's going to say select the regions for the boundary conditions. Well, I know that I want to fix node 1 over here, and then I want to come over here, and I want to fix node 2 as well. So as we can see, I now have node 1 highlighted, as well as I have node 2 highlighted. So after I'm done selecting, I click done, and it appeared on the other screen, but we have this menu right here, which basically says, which degrees of freedom do you want to fix? Well, for both of these nodes, I know I want to fix U1, which is the horizontal direction, and I want to fix U2, which is the vertical direction. This UR3 is basically the rotation, but these type of elements here, these solid type of elements, they do not have degrees of freedom relating to rotation. So you guys can click it on, you can click it off. It's actually not going to make a difference in your analysis. But if I were to have it on, ABAQUS will actually give you a warning, say, hey, you are trying to restrict some degrees of freedom that this element does not even have. So if we don't want that warning sign, we'll just keep it off. So after I do that, I go OK. And as we can see, ABAQUS kind of gives us a nice little picture saying, hey, we were able to fix those two nodes. So those are going to be our two boundary conditions. So now we can move on to the actual loading of this element. And we said that we had 3 different loads that we had to consider. The first one is gravity. The second one is a concentrated load at node 3. And then the last one is a traction vector along this surface over here. So we're going to start off with a simple one, and that's going to be the concentrated loads at node number 3. We said we had a concentrated load of 2 in the vertical direction and a concentrated load of 2 in the horizontal direction. So to do that, I can go down to the load button over here, or I can click over here, create load. Either way, it's going to give you the same menu. And for the loading, of course, it has to be in the step load elements. Remember, that initial step is just for boundary conditions, and we can't have a load boundary condition. So we actually have to put this in our step load element. And what this load is going to be is our concentrated loads. So I'm going to call it concentrated loads. And under all these different options, we can pick concentrated force. That's exactly what we want. So we click continue, and it says select the point for the load. Well, we know we want it to go at node 3 over here, so I'm going to click node 3. I'm going to go done, and then this menu pops up over here. And this basically says what is going to be the component in the horizontal direction. Well, we said that's 2. And what is going to be the component in the vertical direction? Well, we also said that that is going to be 2. So if I click that, OK, as we can see, we now have our load over here applied, looking pretty nice. So the next load that we want to apply is we said that we want a traction vector going along this surface, or basically a distributed load along this element surface over here. So I'm going to expand our loads tab just so we can keep track, and I'm going to double click it again to create a second load. So the second load we are going to call traction vector, nice and simple. And this can actually be done using the surface traction command. So I'm going to go down here, we have surface traction. I'm going to click continue, and then it says select the surfaces for the load. Well, we know that we want it going across this surface over here, so I'm going to click it. As we can see, it is now highlighted. I go done, and then this menu pops up over here. So this is where things probably get a little bit confusing to most students, but don't worry, we are going to go through it together, and hopefully it'll make sense. So the first thing that we want is we don't want shear traction. We just want a simple distributed load. So to do that, we are actually going to go general. All right, general right here, nice and simple. And then we want to define basically 2 different things. The first one is going to be what is the magnitude of that distributed load? And then the second one is going to be basically which direction is the distributed load going, and that's going to go up here. So the magnitude of the load we know is 1. So this is something that we can fill out right away. We know that the magnitude of that distributed load is 1. Now the tricky part comes in the fact that we know that the distributed load is going horizontally to the left. So it's kind of going in this direction. So what we need to do is we need to create a vector showing that direction. So I'm going to go vector over here required, and it says pick the first point of the direction vector. So what I normally do is I just keep this equal to 0, 0, this point over here. I go enter, and it says pick the second point of this vector. So what I'm going to do is I'm going to pick a point directly to the left of this point, because again, we're not actually creating any sort of vector that's meaningful. We just want a vector that has the exact same direction as our distributed load. So if I were to go -1, 0, what this basically means for this vector is that it starts here and it goes directly horizontally to the left. And that's exactly what I want with my distributed load. I want it going directly horizontally to the left. So if I were to go enter, our vector is now defined, our magnitude is now defined. So if I go OK, as we can see, we now have this traction vector going directly to the left. If you guys want to, and you guys are very comfortable with knowing the thickness of our element, we can also apply this as a pressure. But a pressure is kind of more difficult because it's always going to be normal to the surface. As we can see, our distributed load is going perfectly horizontal. It's actually not normal to the surface. So in this case, we can't actually apply a pressure. But if this was perfectly vertical, this surface, then we can actually just apply a pressure, make our lives a little bit easier. So now we have our concentrated load, we have our distributed load. The last thing that we have left to do is our gravity load. So I'm going to come down here. I'm going to say load 3 is going to be our gravity load. And we have two different options here. Two different options, guys. So this is going to be completely up to you. One is we can define it as a body force. So remember that in our analysis, we actually defined it as a body force. We called it a body force, but we said, well, actually, this is going to be gravity. Or in ABAQUS, we can actually just define it as gravity. And here's where the differences are going to rely upon. This gravity right here, we're going to input an acceleration. So remember, when we define the material, we define the density, all right? We define the density of the material, and then under our load here, we would define the acceleration of gravity. So what ABAQUS is going to do, it's going to take that density, it's going to take the gravity, and then it's going to combine it to create basically a body force. So this is one option that we can do. So if I were to select gravity right now, what I would do is I would say, all right, well, in the horizontal direction, it's nothing. And in the vertical direction, we said our gravity is -1. So this is one of the things that we can do. And this would work just fine. So if I were to go this right here and zoom out, as we can see, we kind of have this downward arrow right here, which means that this element now is going to be subjected to gravity. And based on the density of the element, it'll figure out what the body forces are. Now, if we want to, we can actually say, well, you know what? Instead of gravity, we can do things a little bit different. What I can do is I can go, load is going to be gravity, but instead of gravity, we can apply it as a body force. All right, a body force. So I'm going to go continue, and it's going to say select the bodies for this load while we want to apply it over our element. We're going to click done, and then we get this menu over here. Now it looks exactly the same as the other menu, exactly the same, but there are going to be some differences. In our other menu for gravity, we inputted the acceleration of gravity. In this menu right here, we actually input the body forces itself. Now, the body forces are going to have units of force divided by distance cubed. All right, it's not going to be acceleration anymore. So a good example is what I did in my assignment for my students is I gave them a density of 2400 and I gave them a gravity load of 9.81 meters per second squared. So if you guys were to do this in the assignment using the gravity command, then in the density you'd put 2400, and then in the gravity command you would put 9.81. But if we're doing this body force command, what we'd actually have to do is we'd have to take that 2400 and multiply it by 9.81. So basically in this command right here, we have to figure out the body force, which is going to be rho multiplied by b. So it doesn't matter, you guys can do it either way, you're going to get the exact same answer, but I'll just keep it as a body force because I have it opened. So in our particular example, our density was 1 and our gravity was -1. So all we're going to do here is simply go -1. Now again, this would be basically -1 force divided by distance cubed, something like that. So this is not just the acceleration, this is the actual body force. So I click OK, and then this pops up over here. So it looks a little bit different than if I were to use the gravity load command, but in essence, we are still getting the exact same thing. So if we were to look at our element now, we have absolutely everything we need in terms of loading. We have our concentrated load, we have our distributed load, which is a traction vector, and then we have our gravity load, which was defined as a body force. Now remember, you guys can also define it as gravity itself. It's completely up to you guys. So if we were to go to our module command, the last thing that we have basically before we can submit is this mesh command right here. So right now, ABAQUS doesn't know if that this is an element. Again, ABAQUS just kind of say, all right, this is a shape, but I'm not sure how many elements are in the shape. So what we have to do is we have to actually specify that this is just one single element. Because if I were to go to ABAQUS and click this mesh part, oops, sorry. So it's trying to mesh the model. We want to just mesh the part. So if I were to mesh it by ABAQUS as default, as we can see, it throws in a lot of elements. We don't want this. We want to show ABAQUS that this is actually just one single element. So how do we do that? Well, we go to this seed part command. So as we can see, ABAQUS by default tried to pick decent location for all the nodes. But we're going to say, well, you know what? This is only going to be one element. So I'm going to pick a very large seed size. So I'm just going to say it's equal to 4. And it's going to say, you already have a mesh. Do you want to delete it? Yes, we want to delete it. So now what ABAQUS is doing when I did such a large mesh size is say, all right, I'm going to have a node here, a node here, a node here, and then a node over here. That's exactly what we want. So we're going to go OK. Now when we mesh the part, OK to mesh part, yes, we can see that we have just one single element. Now this is nice because you guys can actually pick. So let's say that we wanted 2 elements going across. Well, we know that this distance is roughly 3.5. So if I go something like 2, go apply, delete our mesh, we can see that ABAQUS would now put in that kind of that little extra element there. But again, for our particular example, we just want to deal with one element. So I'm going to go back to one element. And then the last thing that we have to do is specify the element type. Remember, one of the first things that we did in our linear assignment or linear analysis in Mathematica is we said, are we dealing with plane stress or are we dealing with plane strain? And then later on, we said, are we doing full integration or are we doing reduced integration? So all of those controls are actually found in this button right here, which says assign element type. So I'm going to click that. It's going to basically say down here, select the data, and that's because the menu popped up on the other screen. And this is basically all of our element controls. So if we were to scroll down in this family over here, we by default are at plane stress. Now our analysis is plane stress, so we're actually good to go. If we wanted plane strain, we'd have to come up to plane strain. But we said that we want plane stress, we're good to go. Now another thing that we said though, is that we were actually doing full integration. ABAQUS by default will have it as reduced integration. We don't want reduced integration. We want that full integration. So I'm just going to simply unclick reduced integration. So now we have a plane stress element. It is full integration and it is a 4-node quadrilateral element. If I wanted an 8-node, I would select quadratic, but I want it as 4-node. So we're good to go. I'm going to click OK. It is now assigned it into this element, but just to be sure, I like to just mesh the part again, just to be sure. I don't think that actually plays a big impact. So by this point, we have defined absolutely everything we need. So what I'm going to do is I'm going to come down and I'm going to go to the job menu. And the job menu, although it looks pretty scary, it's the nicest of them all. It's basically where you just submit the analysis. So to create the job or to create the analysis, we can click the button, create job, or we can double click job down here. And it says, what do you want to call it? Well, let's just call this element analysis 1. Nice and simple. Click continue. Unless you know what you're doing, I don't recommend playing around with this. So we're just going to go OK. And if I were to go to my job tab and expand it, we now have element analysis 1. Now, what we're going to do is we're going to submit this analysis. So what we do is we click it, we then right click it, and then we go submit. So we just right click it, go submit, nice and simple. As we can see, ABAQUS is starting to run down here. So what it's doing right now is it's taking everything that we've defined, creating a nice file, which has all the information of our model. And then after the file is done, it submits it into the solver. So this running part is after the file is now submitted into the solver. And then after it's done solving it, it will say complete just like this. Now, by default, we are not given our results. So what we have to do is we have to click the job after it's been completed, right click again, and then we go down to results. So if I were to click results right here, this is our element in its undeformed configuration. But if I want to see what happens after all those loads are applied, we simply click this button right here, plot contours on the deformed shape. So we have our deformed shape over here, but if we want to start analyzing what's inside, we can click this plot contours. Now by default, it will always go to the von Mises stress, but we can modify it to basically pick whatever we want. So now what we're going to do is we're going to take those results that we had in Mathematica, and we are going to directly compare it to our ABAQUS results. So two of the most important things that we solved for off the bat were the nodal displacements as well as the reaction forces. So if I want to look at my nodal displacements first, I go up to this property over here, and this is basically what is being plotted. So by default, it's on stress, and more specifically, the von Mises stress. So I'm going to click this over here, and down here we see that we have U, and U basically means displacement. So I'm going to click U over here, and then right now it's doing the magnitude of the displacement, but I'm concerned with, let's say, the horizontal displacement. So I'm going to go U1. Now right here, this is going to be the horizontal displacement along my element. But what I'm going to do is I'm going to compare it to Mathematica, and recall that in Mathematica we have the displacements at the 4 nodes. So to check the displacements at the 4 nodes, I'm going to go down to Tools up top, and then Query, and then I'm going to go Probe Values. I'm going to click Probe Values, and then I get this menu over here. It's a little bit big, so let's try and just make it a little bit smaller so we can still see our elements. It's not working as well, but I guess that'll be fine. All right, so then what we're going to do by default, ABAQUS has it set on elements. Now, we're not concerned with the displacement of the element right now. We're concerned with the displacement at the nodes. So I'm going to go to the drop-down menu, and from elements, I'm going to select nodes. And then now basically I can just go around each of the nodes. And as we can see, if I highlight over a node, ABAQUS will then give us the displacement. So now I'm going to show the displacement we obtained in Mathematica on the screen, and we are just going to go down all of the horizontal displacements first. So at node 1, we get that it's essentially equal to 0. It makes sense, it's fixed. In Mathematica, we had that it's equal to 0. Moving on to node 2, again, essentially equal to 0 because we fixed it, and in Mathematica, we have it equal to 0. Now node 3 over here, we know it's not going to be equal to 0 because we actually displaced it. So if I were to go to ABAQUS, we can see that it is 1.18986. Now if we look at Mathematica, we had 1.19. But that's only because I used 3 significant digits in Mathematica. If I were to do more, as we can see, it is the exact same. Now finally, we'll move on to node 4 at the corner here, and we can see that we get negative 1.254 in ABAQUS, and in Mathematica we have negative 1.25. Again, if I included more significant digits in Mathematica, it would be exactly precise. Now that was the horizontal displacement U1. If I want to look at the vertical displacement, I simply go U1, and I change this over to U2. If I were to go to node 3 over here, it says that it has a vertical displacement of 1.112. If we look at Mathematica, we have it as 1.11. Exactly the same. Moving on to node 4, we can see that the displacement here is negative 3.641. We look at Mathematica, we have negative 3.64. Again, exactly the same. So in terms of displacements, our Mathematica analysis and our ABAQUS analysis are exactly the same. But now let's look at something else. We said, all right, the displacements are good, but we also solve for those reaction forces. So now I'm going to go down to RF, which is reaction forces. And again, it'll go to magnitude by default, but we're going to look at reaction force 1. And let's see how these compare with our Mathematica analysis. So I'm going to scroll down here to node number 2. And as we can see, node number 2, it has negative 0.478 in ABAQUS. And if we look at Mathematica, we have negative 0.478. If I were to look at the horizontal reaction force at node 2, I get, I was going to say negative, but it's not negative. I get 0.734. Look at Mathematica, I have 0.734. So if I were to go, all right, well, that's in the horizontal direction. What about the vertical direction? Reaction force 2. In ABAQUS, I get 2.854. In Mathematica, I get 2.85. And that's, again, only because I suppressed some of those extra digits. Looking at node 2 over here, I get 2.646. In Mathematica, I have 2.65. Which again, suppress some digits, otherwise they are the exact same. So in terms of reaction forces as well as nodal displacements, we have the exact same results from ABAQUS as we did with Mathematica. Now, how about the stresses? So if I were to go down here, or actually let's start with the strains. E right here, this is going to be our strains. And what we're going to do is we are going to look at E11. So remember that in Mathematica, we said that we basically have the stress at every point in our stresses and the strains in every point in our element. So what we did to make it simpler is we just look at the strains at our integration points. So how do we do that in ABAQUS? Well, Right now we're back on nodes, but we know that we want to go back to element. So I'm going to switch this to element, and by default, it'll have integration point selected kind of as a default. So if we're looking at strain 1, 1 in our elements at our integration points, and I were to click, then basically this is going to be our 4 strains at the 4 integration points. Now, if we were to compare this to our Mathematica results, the first one here is 0.689, while in Mathematica we have 0.69. The second result, 0.2568, blah, blah, blah. In Mathematica, we have 0.257. Next result, we have 0.6237. Mathematica, we have 0.624. It's very simple to see that these are all going to be the exact same. And that's going to be true. Oops, yes, I do want to clear that. And that's going to be true for all of our strains. So if I were to do this with E22 as well as E12, which we also calculate in Mathematica, they are going to be exactly the same. How about stresses though? So if I were to go to stresses, which is S, and go down to S11, and I were to probe those values again at the element, at the integration points, and I were to click it, we can see that ABAQUS gives us 0.369. In Mathematica, we have 0.369. Our second entry is negative 0.061. In Mathematica, we have negative 0.061. So as we can see, the stresses are all identical as well. So that's it for kind of harassing this element and probing it. And I just want to show you guys that everything that we did in Mathematica there, that is exactly what is going on in our actual finite element analysis. Everything checks out, everything is the exact same. So now when you guys do your guys' analysis by yourself, you guys have a good understanding of what exactly ABAQUS is doing in the background to get these numbers, to get these stresses, to get these strains, etc., etc. So that's going to be it for this video, guys. I hope I was able to help you guys learn something about linear analysis, maybe shed some light on it. I know at first it can be really confusing, so that's why I'm here trying to make it as less confusing as possible for you guys. So again, that's it for this video. I hope you guys have a wonderful day. Thank you guys so much for listening. I will see you guys in the next example video.